Join me as I dive deep into the question, could bird flu be the next global pandemic? Let's find out together. The US has seen sporadic human cases of avian influenza A, H5N1, primarily linked to occupational exposure to infected animals. In late March 2024, a case was identified in a person exposed to dairy cows suspected of carrying the virus, with additional sporadic cases reported in May 2024. These incidents underline the risk to those with job-related or recreational exposure to birds or infected mammals, although the general public's risk remains low. The US has also documented 4 human infections with low pathogenic avian influenza A, H7N2, causing mild to moderate illness. Despite these occurrences, there's no evidence of sustained human-to-human transmission of the current H5N1 strains, and the situation is primarily an animal health issue. However, the CDC continues to monitor for any changes that might increase human health risks, such as multiple simultaneous human infections or person-to-person spread. In contrast, the 2009 H1N1 influenza virus, known as H1N1, posed a significant global health challenge. First detected in the US, this novel virus spread rapidly worldwide due to its unique genetic makeup, which differed from other circulating H1N1 viruses. This lack of cross-immunity meant that seasonal flu vaccines were ineffective against it, leading to a significant health impact. From April 2009 to April 2010, approximately 60 million cases, 274,000 hospitalizations, and 12,000 deaths were estimated in the US alone. Globally, the virus was estimated to have caused between 100 to 500,000 deaths in its first year. Unlike typical seasonal flu, which predominantly affects the elderly, this pandemic saw 80% of deaths in people under 65. The severity of the 2009 H1N1 flu was significantly less than historical pandemics like the 1918 flu, with mortality rates at about 0.001% to 0.007% of the world's population. The response in the US was comprehensive, involving public health measures, vaccine development, and global coordination. Although the WHO declared the end of the pandemic in August 2010, the H1N1 virus integrated into seasonal flu strains, continuing to affect global health annually. The process by which avian influenza, commonly known as bird flu, could mutate to become transmissible among humans involves several biological mechanisms, drawing parallels with how seasonal influenza viruses evolve. First, let's discuss genetic mutations and receptor binding. Avian influenza viruses typically bind to sialic acid receptors with an alpha-2,3 linkage, which are prevalent in the gastrointestinal tracts of birds. For efficient human-to-human transmission, the virus needs to adapt to bind to the alpha-2,6-linked sialic acid receptors found predominantly in the human upper respiratory tract. This shift can occur through mutations in the hemagglutinin (HA) protein, particularly at the receptor binding site, RBS. For instance, the E627K mutation in the PB2 gene has been associated with increased virulence in mammals. Just as with seasonal flu, where minor mutations, antigenic drift, occur continuously, avian flu viruses can accumulate genetic changes over time. If these mutations enhance the virus's ability to replicate in human cells or bind to human receptors more effectively, it could lead to a strain capable of sustained human transmission. Now let's discuss reassortment. Influenza viruses have segmented genomes, which allows for reassortment when 2 different strains infect the same host cell. Pigs, for instance, have both alpha-2,3 and alpha-2,6 receptors, making them an ideal mixing vessel for avian and human flu viruses. If an avian flu virus reassorts with a human flu virus in such a host, the resulting hybrid could have genes from both, potentially enabling human-to-human transmission. This was the case with the 2009 H1N1 pandemic, where reassortment occurred in pigs before jumping to humans. A famous example from history is the 1918 Spanish flu is believed to have originated from an avian source, possibly through reassortment with human strains, leading to a virus capable of efficient human-to-human spread. What about adaptation to human hosts? Seasonal flu viruses adapt over time to replicate more efficiently in human cells. Similarly, for bird flu to become transmissible among humans, mutations must enhance the virus's ability to replicate in the human respiratory tract. This might involve changes in polymerase genes or other viral proteins that interact with human cellular machinery. The virus might also evolve mechanisms to evade human immune responses, similar to how seasonal flu viruses change their surface proteins, hemagglutinin and neuraminidase, to avoid recognition by human antibodies. There are some parallels with seasonal flu. Each flu season, the influenza virus undergoes antigenic drift, leading to small changes that help it escape immunity from previous infections or vaccinations. This process is similar to what avian flu would need to undergo to become a human-transmissible pathogen. Seasonal flu often originates from animal reservoirs, like pigs or birds, before acquiring the mutations needed for human adaptation. This cross-species jump is facilitated by close human-animal interactions or through intermediate hosts where reassortment can occur. Public health vigilance is needed. Continuous monitoring of flu strains in both animal and human populations is crucial. This vigilance allows for the early detection of viruses showing signs of adaptation to human hosts, similar to how we monitor for new seasonal flu strains each year. Just as annual flu vaccines are updated to match circulating strains, rapid vaccine development could be initiated if a bird flu strain showed signs of becoming human adaptable. In summary, for bird flu to mutate into a form transmissible among humans, it would likely need a combination of mutations that change its receptor specificity, enhance replication in human cells, and potentially involve reassortment events in intermediate hosts like pigs. These mechanisms mirror the evolutionary processes seen in seasonal influenza, where genetic drift and shift allow the virus to adapt to human hosts year after year. The current avian flu situation in humans, primarily an issue in occupational settings, contrasts sharply with the widespread human impact of the 2009 H1N1 pandemic. While the H5N1 virus does not currently show signs of becoming a human pandemic threat, the lessons from 2009 underscore the importance of vigilance, preparedness, and rapid response in managing influenza outbreaks.